Hello, everybody. Welcome to this month's EMBL-ABR webinar, which will be about Snakemake and its use in reproducible and scalable bioinformatics workflows. My name's Jeff Christensen, and I'm from the Queensland Cyber Infrastructure Foundation, or QCIF, and we're a node of EMBL-ABR. I'll be your host for today. My colleague Susanna Bacon from ARDC is behind the scenes, also co-hosting this webinar with me. EMBL-ABR is a distributed national research infrastructure network that provides bioinformatics support to life science researchers in Australia. It was set up as a collaboration with the EBI, or the European Bioinformatics Institute in Europe, to maximise Australia's bioinformatics capability. There are currently 13 nodes of EMBL-ABR across Australia, and each of which undertake or support bioinformatics research around several key areas. These are shown on the right. They're data, tools, compute, training, standards, and platforms. Before continuing, I'll mention a few housekeeping things for today's webinar. So all attendees, our microphones are muted during the presentation, and this is to minimize background noise when Nathan is speaking. If you do have a question, please type it into the question box in the GoToWebinar software. I'll be looking at the questions, and at the end of the presentation, in the last 10 minutes, I'll relay these to Nathan. This particular broadcast will be recorded and we'll make it available on the EMBL-ABR YouTube channel. The URL is shown at the bottom of the page there. We'll notify all registrants when this recording is available. So today we're very happy to have Nathan Watson-Haig speaking to us. Nathan's a senior bioinformatician at the Bioinformatics Hub at the University of Adelaide, and he has over 15 years' experience in the field of bioinformatics with expertise in a huge range of topics, including genomics, transcriptomics, pipeline development, high performance, and cloud computing. During his PhD, Nathan investigated the location of the root, the oldest part of the eukaryotic tree of life. At this time, he was also exposed to high performance computing infrastructure and first became involved in open source projects. He followed this up with a bioinformatics postdoc looking at range margins of an Arabidopsis species, where he analysed microarray data, as well as integrating data sets from transcriptomics, metabolomics, proteomics, population genetics, and ecological studies. He subsequently held research positions at a number of Australian institutions, including CSIRO, the Australian Wine Research Institute, and most recently at the Australian Centre for Plant Functional Genomics in the School of Agriculture, Food and Wine at the University of Adelaide. Here he was playing a pivotal role in the development and application of analytical approaches and pipelines to NGS-based wheat genomics data sets. And he was responsible for setting up and managing the Linux-based scientific computing infrastructure, including several large memory compute nodes configured as a Salome cluster, hundreds of terabytes of clustered file system storage, and around 24 virtual machines. Nathan also has had extensive involvement in national training, bioinformatics training efforts, and community building locally, nationally, and internationally. Today in this webinar, we'll be exploring the key features of Snakemake, taking a look at the core concepts and examples required for making your first steps into reproducible Snakemake workflows. And then building on this foundation, Nathan will introduce some more advanced features which enable workflows to scale seamlessly to server, cluster, grid, and cloud environments, as well as to different software execution environments. So now I will hand over to Nathan and make you the presenter. And I will mute myself. Thanks, Nathan.
Thanks, Jeff, for the introduction. Okay, thanks for attending, everybody. So today I'm going to talk about Snakemake, reproducible and scalable bioinformatic workflows. This here is just a bit for posterity, really, and a link to a GitHub repository with the PowerPoint, as well as code that you can use after this workshop, potentially to work through some of the examples that I'll be presenting today. So I thought I'd start with usually the types of pipelines that people, bioinformaticians, tend to use before moving into how Snakemake can address some of the challenges. So typically what I find is that people will be working on a cluster, and that's usually because they're working on problems that are much larger than what could be handled, say, by a desktop computer. So this is sort of a prerequisite to essentially what I'm talking about today. And typically people are working across one of these resource management systems. Locally here, we have a HPC system at the university that uses Slurm, but there are other resource management systems that are in use on other HPC facilities. And whilst the examples that I show here are a bit more specific and set up for Slurm, it's also possible to configure workflows to work in these other environments. Typically what people have, I find, is that they'll usually have a pipeline that's developed that consists usually of a single script or a small number of scripts, which they then submit to a cluster that then queues and waits for the resources that are required, and after some time that will get executed. Typically these things do more than one task. For example, they might do read QC, read trimming, read alignment, and any other sort of downstream subsequent steps. And this raises a few issues because quite often this is sort of executed in serial, and there's quite often loops in there to loop over files, and this sort of presents a few problems. It's not easy to ensure that commands are completed successfully before continuing with a subsequent task that is dependent on it, unless you do a lot of coding around the commands. Quite often, getting the resource requirements right for a job that's submitted to the cluster is quite difficult, and then they usually end up being over-specified. So for example, you just say, okay, I need 200 gigs of RAM, so I'll put that in as a requirement. However, when the job actually runs, you may find out that actually you only needed 50 gigs of RAM. This has problems, and I'll come on to that shortly. Also, with these types of scripts, it's very difficult to rerun parts of the pipeline. So for instance, if one part fails, it's difficult to go back and rerun it in isolation. And people will end up sort of commenting out lines of code that they want to skip over and resubmitting that same script to Slurm or PBS or such. So the way that I usually think about this is that this box here represents some resource requirements for your script that you've submitted. And within that, you have a bunch of different tasks, different processes, commands that you execute as part of that script. And in this case here, we have 10 or so different processes that are all executed in serial, but are all very similar. So for instance, looping over files. Then you might have part of the script that has a large memory requirement, a large CPU that can be highly parallelized. And so this resource, this particular command requires more resources. And this is usually what then dictates the resources that are requested for a particular script submitted to the cluster. And what you end up with is all of this white space here is representing this idle, unused compute resources. The consequence of this is that you are over-specifying the resources for your entire pipeline, and this big block, the dotted lines, ends up being queued in the system for a period of time until such all of that resource is available to run the script. And once that then is started executing on the cluster, you then have all of this unused resources depending on which part of the pipeline is in. So all of this is basically results in delays in getting a script to completion. And in my situation, this can lead to quite significant delays because of quite large resource requirements. Again, I'll come back to that in a moment. So why have a workflow management system? And there are many out there. I think probably the two that are most common is probably Snakemake and Nextflow. So I'm talking about Snakemake today. And the idea really behind a workflow management system is that it's able to parallelize the tasks that are required. It can take care of suspending, resuming jobs that fail for whatever reason, so that you don't have to faff around with resubmitting just small chunks of your code and needlessly rerunning things that were successful previously. They usually also take care of logging, and data provenance is usually quite a big feature of these things, so that you have a record of what was done. You can potentially then reuse that workflow at some future date in time, and other users can take that pipeline and rerun it. To be able to do this high sort of level of parallelization, it's very often in the case of the script that I mentioned previously, where you've got lots of processes that are and commands that are being executed one after the other. In a workflow system, you need to think about breaking those pipeline down into individual tasks. So in this way, I always think about the Unix philosophy, which is writing programs, or in workflow management, these would be tasks. To do one thing and to do it well, don't have a task that does a multitude of different things, and write these tasks so that they work together. And this sort of comes naturally with a workflow management system that knows how to link together tasks. So my main drivers for using Snakemake was that I had a bit of a history with using GNU Make for developing pipelines, thanks to sort of software carpentry. And there's, if anyone's ever used GNU Make for pipelines, there's quite a few limitations to how you can develop those pipelines, and it can become a bit of a drag quite quickly. So Snakemake was a sort of logical fit into the same ethos as GNU Make, so it felt natural to be starting to use Snakemake for me. But more generally, my big drivers for using something like this is that a lot of my work is research is done in Wheat, which, for those who don't know, is a 16 gigabase pair hexaploid. So any sort of analyses in Wheat can be very time consuming. So you want to parallelize tasks to get jobs done faster as much as possible. If a task fails, you only want to redo those that actually failed and not have to redo things that didn't. And so having a workflow system that's able to do that is really beneficial. Want to have efficient HPC resource utilization, because many HPC systems are oversubscribed and you don't want to be queuing needlessly in the queues. You want to get jobs in there quickly, have them processed and get your results out. Data provenance, again, having a record of what was done is really important, and that sort of goes hand in hand with reproducibility, so that either I can redo an analysis later on or reuse my workflow for another project, and similarly for other people that I maybe haven't even met before. So moving on to Snakemake. Essentially, Snakemake is you decompose a workflow into individual rules. And so you have a rule followed by the name of the rule. And then these rules define how to create given output, here specified by this output keyword. In this case, it's mapped.my.bam. How to create that file from some input files. And so you specify these input files. And these can contain names, to allow you to refer to individual files explicitly. And then in this case, we have a shell keyword that specifies the shell command that will get executed in order to generate the output file from the input files. So Snakemake then takes all of this information and builds a dependency graph and determines an execution order for all of the rules. And so when you come to actually executing Snakemake, you tell Snakemake which files, or in Snakemake language, targets you want to create. And with these rules that are defined in a Snake file, Snakemake will figure out how to get to that target based on all of the rules that have been defined, and generate all of the intermediate files that might be required on the path to generating that target. So by default, as in GNU Make, the first rule gets executed, irrespective of what's it called, if you don't say what target you want. So this gives rise to this pseudo rule at the start of a snake file that allows you to create a list of files or targets that you want to create. And this is usually conveniently called all, as in the GNU Make as well. So for instance, this would be at the top of one of my snake files. I have this rule that I call all by convention, and its input are all of the target files I actually want the pipeline to create. So in this case, if I executed this snake file, it would automatically say, okay, I need to make these two files mapped acbarry.bam and mapped alson.bam. And it will then figure out how to go about doing that from any other remaining rules that are defined in the snake file. There's this extra bit of decoration here at the top of the snake file here, which is a way to specify that if I'm going to execute these rules on a cluster, I actually want this list of rules to be executed locally on my sort of head node, rather than actually being submitted to the cluster as a separate job. Specifying more than a few files here can be quite laborious if you've got lots of files that you want to generate. So Snakemake has this expand function, which helps you to reduce the level of repetition. And its syntax looks something like this, where expand here you have a variable called accession, and it is expanded from this array. This array here can be defined in line as it's shown, or you can specify it in the main body of the Snakemake file. If you have a rule like this, it's hard-coded that these are the output files and these are the input files. So in this case, my is a sort of common prefix to this rule, and we can generalize this using wildcards. So here you use curly braces and then a wildcard name. So this is anything you want, and it's what you can refer to in other parts of the rule. So the advantage behind this is now this rule knows how to make a multitude of files where sample will be set to this bolded text within these files. So up to now, I've shown some rules that have a shell keyword and has the bash or shell commands in there that will be executed to generate the output file from the defined input. Snakemake also has the capability to use other scripts, which uses this script keyword. By default, Snakemake supports Python, R and R Markdown files. You'll also see in some of the Snakemake documentation that it also supports its run, which is for use for Python script. However, it's advised not to use Python script in one of these run blocks because it has some constraints on other things that you might like to do with Snakemake, which we might touch on later. So it's advisable, instead of using the run keyword, is to use the script and supply the Python script to it instead. As you can imagine, there are lots of rules that will be generalizable. Doing GATK haplotype calling is one of those tasks that has some common types of inputs and has an output. And so Snakemake has this wrappers keyword that allows you to reference sort of generalized wrapper scripts that are maintained in a Snakemake wrappers repository. It also supports the common workflow language, again for reuse. However, for reproducibility, these links really should have the Git hash in there so that you can always run the same workflow in future. Using CWL also imposes some additional restrictions on how you specify the input-output parameters for the rule. I haven't personally played around with this yet, so I can't really comment too much more. Okay, so that gives you a bit of a flavour for the how you develop these rules and how you specify them. My typical workflow is to start with a rule with hard-coded paths for files, and then I'll do a step of generalizations to abstract out some of the variables. And typically I use shell keywords and rather than some of these other keywords like the script and CWL. Okay. So the installation of Snakemake is generally recommended to use Conda. So for those of you who haven't used Conda previously, if you're working on a HPC facility, they tend to have Conda, Anaconda available. These are typically accessible through the modules system, so something like this might work on your cluster. And then you can create the Conda environment with Snakemake installed within it using a command like this. Once you've set up that environment, typically you come back at a later date or a few minutes after creating the environment, you'll need to load the Anaconda module again, and then you activate the Snakemake environment. So for the remainder of this talk, what I am going to go through is some example data sets. This is all part of this repository here, so you can have a look at this after the webinar and work your way through. So just out of interest and a bit of a sidetrack, the part of this workflow is to actually extract out a subset of data from some public data that was recently published in the Dawn paper that I authored. And what we're actually looking at is a 58 kilobase pair region of a chromosome in wheat. And it was of interest because there are two genes which are affected by a deletion in some accessions of wheat. You can read the Dawn paper if you're interested. But this is just to say the workflow will be setting up this small mock data set for the purpose of this workflow. So Snakemake, by default, without telling it which file to use, will look for the rules in a file called snakefile. And we can, with this repository, there is a snakefile available with all of the rules specified. And if we execute a command like this with the DAG argument, it will generate a direct acyclic graph of the jobs and their dependencies. So this is what this would look like. So straight out of the box, we have nodes represent jobs that will get executed. Within each of these, you'll see that there's the rule name as well as wildcard name value pairs. The arrows represent job dependencies. And here down at the bottom is the target. So this is that all target, the default first rule that Snakemake is trying to drive towards creating that target. So the repository, if you clone it, will just have a single wheat accession called AC Barry specified in it. And you can see that here and all of the downstream rules and jobs that will get executed for that particular accession. We can do a dry run of Snakemake and see what shell commands would be executed by running a command such as this. However, what's probably more useful is knowing how to execute this workflow for real and submitting all of the jobs to a cluster backend. And the commands that I'm going to show will actually use the Conda software environment and set these up within a Singularity container. And depending on timing, I may get to a bit more information later. So again, here I'm loading this Singularity to make that available to Snakemake. and I'm executing Snakemake here with a bunch of parameters. One of these profile is some predefined files that's with this repository that allows Snakemake to communicate with the Slurm cluster. And there's some cluster configuration files here that determine what resources will be allocated to each job. And we're specifying also here that we want to use Singularity and use Conda software environments. So at the top of the Snake file, if you go and have a look at this after the webinar, you'll see that there's an array defined, and by default, it's just got a single accession in there, AC Barry. If we added in another one here, say Alson, we can run through some of these steps again, and we'll have a look at the job dependency graph next. And so you see that this is now bigger, and what you see here is that here's our new accession with the key value pair Alson in there. You'll notice that the lines around these jobs are different now. So if we'd submitted the workflow to the cluster and jobs completed, the dashed lines basically mean these jobs have been completed and won't be rerun. Solid line means that these jobs are the ones that still need to be run. And so you can see here, you can incrementally add in new data, new accessions, and Snakemake will only run those parts of the workflow that are required and not rerun things that don't need it. You'll see the color of the nodes here correspond to the same rules. So this just helps orient you a little bit in terms of what rules are being executed. And so if we go back to if we execute that, we'll get all of the jobs submitted to the queue. And we can also then expand this and say, add even more accessions. And so this is adding all of the accessions that were available to Dawn. And if we again have a look at the graph for that, these graphs start getting quite big quite quickly and almost become useless at this stage. So there is also another graph that you can produce, which is a graph of the rules rather than a graph of the jobs. So this is a simplified, this generates a more simplified graph structure, but it doesn't contain the same level of information. Here you just have the rule names and how they depend on each other, not the actual jobs themselves. You can get a summary of what would be done if you execute a command with dry run and quiet. It just gives you a summary of the jobs that would be executed in this situation. So here there's 108 jobs. So before you may have like a script that does all of these steps one after the other sequentially. With Snakemake and breaking these jobs down into individual rules and tasks, you can see now that we're going from a single script now to hundreds of jobs for a relatively small number of samples. So this enables Snakemake to run these jobs in a more highly parallelized fashion and get the job done faster. So if you have these jobs with shell keywords specified, Snakemake, when it runs those jobs, will just assume that those commands are in the path. On HPC systems, that generally isn't the case. You usually have a module system where you have to load modules, or you have Conda where you can specify a Conda environment that sets up what tools need to be installed for a particular job. And so in the example workflow provided in the repository, there is this end tutorial YAML file, which defines what tools are required. And so that looks like this. So this is Conda stuff, which I'm not necessarily going to get into, but this dependency is a list of tools that are required and their versions for executing this job. So these rules, these Conda environments can be specified on a per rule basis. So here and in the rest of the Snake files that are distributed in the repository, these all refer to the same tutorial YAML file. So effectively every rule has the same environment setup. However, that doesn't have to be the case. Each rule can point to a different YAML file, and so you can have a much more trimmed down software environment that each rule operates within. So for instance, this BWA mem, you might only want BWA and SAM tools or something like that specified, and so you can configure it at that level. You can search the Anaconda Cloud website for available tools and versions for putting in these YAML files. Okay, so just to summarize this, previously we had this maybe a single script that executed things serially, and this whole script would potentially be queuing in a system because of the large over specification of resources required, as indicated by this dotted line box. Now, when you use something like Snakemake, that sort of disappears, and you can have these resources specified on a per job. And so things that you might have executed serially as well can be executed in a parallelized fashion. And so not only do the jobs start executing on the cluster sooner, but jobs get executed in parallel, and so you can get to your results much faster. I'm going to advance on to some more advanced features, because we have about 15 minutes. I'm going to talk about rule resources, because I think this is a really nice way that Snakemake allows you to specify what resources each rule requires, and having that information pass through to Slurm so that each job can be customized for its resources. So distributed in the repository is this Slurm profile and a bunch of cluster configuration files, and together they determine what resources each job will get when it's submitted to Slurm. So just as a reminder of how we've been sort of submitting our workflow to a cluster, we do it like this. This cluster config default YAML file sets some default cluster configuration values, and if we specify this cluster config argument multiple times, subsequent values will get overridden. And so Phoenix here is the name of our HPC, so there are some Phoenix specific cluster configuration options in here, and that's mostly account and partition information that will differ between Slurm installations. So to take a look at this file, it looks like this. So default here says to Snakemake that every rule will get this set of values by default unless otherwise overridden. So here we can see that the number of CPUs per task is set to 1, the memory requirement is 200 megabytes, and we've got 5 minutes required for each job. So in the absence of any other information, this is what resources will be requested for each job. It's possible to override these for individual jobs where you use the job name. So the example I've been using throughout is this BWA mem. And so here we can override those defaults and say we want 16 CPUs, we want 10 gigabytes of RAM, and we want an hour of time on the cluster. So this is all well and good for sort of static jobs. However, if your job if you want to apply your workflow to, say, a different species or a different data set which has different volume of data or samples, these resource requirements can go up and down, and having them hard-coded can be a bit inflexible. So Snakemake has this resources keyword that you can use in the job specifications in the Snake file. In this YAML file, in this cluster config YAML file, we can use these variables then rather than hard coding them in there. So it's curly braces again, so it's very common in Snakemake for this. Resources refers to this resources that's specified elsewhere, and I'll show you this file here. and dot, and in this case MB refers to the value within the rule. And so what this allows you to do then is within the snake file you can use this resources keyword and specify how much memory, how much time that rule will require. So this is sort of separating out some of the configuration from the workflow specific information, but it's still all hard coded at this point. One thing to note is that these must be integers as well, and that's important when it comes to the next step, which is trying to scale these values for the runs. Snakemake can make use of Python lambda functions or anonymous functions. They have a particular signature, so when you call them, they have to have wildcards there, but can optionally have input, threads, and attempt. And I'll explain these just in a moment. Important restriction for lambda functions is that it's a single expression, which means that beyond something simple, these expressions can get rather complex and messy and ugly and error prone. And again, I'll show you an example of that. So a simple way of using this dynamic scaling would be to scale up resources for each job each time a job is retried by Snakemake. So the profile that's with this repository will ensure that if a job fails, Snakemake will resubmit that job and attempt to get that job over the line and completed. And it will do this two times, and the attempt number for a particular job is stored in this variable attempt. And what we can do is we could use that to scale up the resources. For instance, if a job potentially fails because the time or the memory allocation isn't high enough, we can use this attempt and this lambda function to dynamically scale these resources. So this is how that would look. So here we've got this lambda function with the wildcards that's required, and we're also wanting to access this attempt variable. So for the memory here, we've got the 10 gigabytes or 10,000 megabytes of RAM, and this will just be simply multiplied by the attempt number. So on the first run, the memory will be 10 gigabytes. On the second subsequent attempt, if a job fails, it'll increment that and it will go to 20 gigabytes, and something similar for the time requirements. So this is a bit of a blunt way of trying to get a job over the line if a failure is potentially due to a lack of resources. You can do something a bit more fine-grained. So in this case here, we are scaling this by attempt number, but we're just simply adding 10% onto the resource requirement for each attempt. So here, the first time, this would equate to 10 gigabytes for the memory and 60 minutes for the runtime. And then the second attempt, that scales up by 10%. And if we increase the attempt number in the profile, then we can also, that will continue on trying to retry jobs when they fail. The next logical step there is that, okay, we have this thing that tries to get jobs over the line if they fail because of resource limitations. However, maybe a more interesting approach is to actually try to generate a resource requirement that is dependent on the input file sizes. So in this case here, I've got an example of taking the size of the input index file or files, depending on how many files are specified by that. We'll sum those and scale them to megabytes, and then add on 10% for each retry. And so this way you can be a bit more intelligent, and this is really useful for when you want to move a workflow from one species to another. So maybe you developed a workflow in bacteria and you suddenly want to work in wheat, which is, you know, much more complex and difficult. This sort of approach will help make that transition more easily. one thing I haven't mentioned is that Snakemake is Python based, and Snake files can contain any sort of arbitrary Python code. I'm not a Python person, I'm more of a Perl person, so Python doesn't come naturally, but you can include code in there, functions and things. One thing that may be interesting is rather than specifying, say, input files, say by sample or by accession, as is this example workflow, you might actually, rather than hard coding it in there, you might actually want to have the workflow and Snakemake determine that based on a directory structure. So if you have a directory structure that allows, you could have it pass that structure to pull out that information. So something like this here, Snakemake provides this glob wildcards, which is a way to glob the directory structure and pass out some information. So this here is basically pulling out files that reside under this raw reads directory. The curly braces there is basically like a capturing mechanism for Snakemake to pull out that part of information, in this case an accession, and there's a regular expression there which constrains how that pattern is matched. Then there's an underscore, capital R, and then there's this other bit here which is extracting out the read, whether it's the R1 or the R2, and it's further constrained by having to be a fastq.gzip file. And so we can use this type of thing to pull that information out of the file system rather than actually having it hard-coded, again, making this sort of thing more portable and reusable. I'm going to skip this. Another pretty cool feature for Snakemake is the ability to do benchmarking. Snakemake provides this benchmark keyword and a function called repeat that allows you to repeat the and rerun the rule and the benchmarking of that run multiple times. So for instance, you can set the number of benchmarks to be 3, and then you can use this benchmark keyword together with a repeat function. You specify the benchmark file name here. This is where the information from the benchmark of this rule will reside after the rule is executed. And this is really good to have a look to see how the time and memory requirements of a particular rule scale, and you could rerun this potentially with different size data sets and get some idea in terms of how those resource requirements scale and feed that back into this dynamic resource allocation that you specify for a rule, so that you can go easily between sort of different projects, different organisms, and so on. This type of information can be passed out, and you could plot this. I have to say thanks to Steve for doing this yesterday for me. I haven't had a chance to incorporate this into the workflow, but because this is written in an R Markdown, this could actually be the output of a rule that uses an R Markdown file to generate these plots. We can use containers for reproducibility. I haven't said much about it, and it's probably out of the scope of this, but you can use singularity argument to say that you want to run these jobs within a singularity container to segregate the execution environment from the underlying sort of operating system. These can take, you can specify these for individual jobs. This supports all of the things that Singularity supports in terms of URL. So it will support Docker and shub URLs. And you can specify these Singularity containers globally for the entire workflow. And as we've shown in the examples previously, the use of Singularity and use Conda results in these Conda environments being set up within this Miniconda Singularity container that's specified in the make file. Depending on the container that you use, the software environment is usually very minimal and trimmed down. So for example, here Miniconda doesn't contain the unzip command, which is required by one of the tools. And so you have to really be explicit about which tools you require for the rules and specify them directly in the Conda environment files. Okay, and that's all for today. Thank you for listening, and I'll take questions via Jeff.
Thanks. So if people want to add questions into the question box, we've got a couple of there, but I just had a quick one to start with. And Nathan, I really liked your illustration at the beginning, sort of demonstrating how, traditional resource allocation requests can be, really inadequate, I guess, from a workflow perspective. But in some sense, setting that up is very easy because you just, specify one resource allocation for the whole job. And this I can see could get very complicated. I guess I was just wondering, as far as you use Snakemake, does a workflow have to sort of get above a sort of level of complexity before you consider it as an option, or is this now your sort of preferred mode of operation when building workflows for your particular HPC systems?
Yeah, that's a good question because the difficulty or complexity of that initial hurdle can be a real barrier to using tools or using new tools. Now, my general approach is that I will generate the input and output specification of the rules and generally hard code them in and just use the shell keyword, because then that means I can quickly and easily put in the shell commands that I would otherwise have been executing elsewhere. So that initial step is really easy and really straightforward. Now, having these profiles set up in the background facilitates the ease with which that can then be easily executed on a cluster environment, which is the most painful bit, I think, about Snakemake. But if that's already set up, then actually defining these rules is really quick and really easy. And so the hurdle there is not very great. Now, the next step then is to generalize that and parameterize some of those rules, which again is not that difficult. But obviously the payoff then will depend on how much you then want to transition this workflow to another project, another data set, and so on. So I mean, for me, I personally go straight into Snakemake for most of my workflows now.
Okay, great. We have a question from Gareth Price, and he would like you to comment on how you save or archive your Snakemake files, because he thinks they would make quite good sort of electronic lab notebooks.
Yep. So there are features for archiving them, making them available to others to use. And I would encourage Gareth to go to the Snakemake documentation for that.
Okay.
But yes, it's possible.
Brilliant. Okay, are there any more? Oh, actually, yes, there are. Okay, we have a question from Davis McCarthy. How does Conda scale with large numbers of jobs when the dependency graph becomes very large? He's run into issues when running Snakemake on tens of thousands of files in a single cell analysis setting. Any suggestions for handling this sort of situation? Nextflow, I understand, doesn't suffer so much from scalability in that respect.
So my understanding, it would be that each job would have its own environment set up. If there's tens of thousands of jobs running in parallel, it could become an issue for the underlying cluster hardware itself if there's lots of simultaneous access to files like the Conda environment files. So that might be where there are some issues. Yeah, maybe I can speak to him afterwards to see exactly where that problem's lying, because I haven't had that issue myself.
Okay, thanks. we can put you in touch. No, not a problem. And we will hear about Nextflow next month as well. And a couple of questions here from Benjamin Speshinger. Can you use regular Python for pulling in the accession numbers instead of the Snakemake glob function?
Yep, so it will take any sort of, you can just throw Python code into the Snake file itself. You can do the import statements for the various Python modules, and you can basically do a lot with Python and just substitute that straight in. You can create Python functions within the body of the Snake file and use that for and call that function within the rules to define, say, the input files for a particular rule. So all of that is readily available and accessible if you're a Python person.
Excellent. We've got probably time for another couple of quick questions. So another one from Benjamin is, how do you handle copying data over to nodes if this is available?
So Snakemake expects there to be a shared file system, so that all nodes have access to the same project working directory. Snakemake can also interact with remote storage providers. So if you want to have files pulled down from different resources through HTTP, FTP, various other different storage backends, you can have jobs that are able to do that. You'll see in the Snake file distributed as part of the repository, there is some of that goes on there for pulling down the reference file and the reads from BAM files for setting up the raw data in this example. So I encourage you to have a look at that. But typically, it would expect the underlying file system to be the same on all nodes.
Okay, fantastic. I think we've run out of time for questions. A couple of people have asked a question about can they get the slides. So if you go to the chat window in GoToWebinar, we've put the link to Nathan's GitHub repository there, and that's got a link to the slides in it. We'll also be putting those into the, we'll be emailing everybody who registered, and that'll be included in that particular email. Okay, well, thanks very much, Nathan. That was fantastic. A lot of other people have said thanks for the webinar. So
you're welcome.
I think we've heard a lot of people that are curious about this. So it's been fantastic. So thanks very much. Just on this particular slide, so I'd just like to let you know that, well, thank you to everyone as well for attending, actually. So if you have any suggestions for future webinar topics or speakers that you'd like to hear, please feel free to drop us an email. The email's on this particular slides. It's webinars@embl-abr.org.au. And if you go to our webinars webpage, you can see our forward webinar schedule for 2019. And that also there's registration links for all of those. So we currently have a few more webinars planned, and we'll be having one every month for the remainder of the year. Next month's webinar will be by Rad Sachecki from Cyro on the 14th of March, and he's going to speak about Nextflow. And that's another tool that can make your workflows more shareable, replicable, and usable across different cloud and compute cluster environments. So thanks to everyone for making the time to attend the webinar today. As I said, it's been recorded. We'll be putting the recording onto our YouTube channel, and we'll be sending out an email to everyone who registered with all of those links and any of the links for what Nathan was referring to today. So finally, we'd just like to acknowledge a few organisations for funding that make this webinar series possible. So EMBL-ABR would like to acknowledge funding from Bioplatforms Australia and the University of Melbourne, and ARDC, who we're partnering with on this webinar program, would like to acknowledge funding from NCRIS. So just as this webinar closes, there'll be a short survey. So it only takes about a minute to fill out. So if you could fill it in, that would be fantastic. So thanks very much, and hope to see you next month. Bye-bye.